Hello, so new topic, convolution. All right, so convolution is a bit of a mysterious operation, but it's also a very important one. So it shows up in lots of different places. So it shows up in approximation theory, and if I remember to do it, and if it kind of fits in naturally, I might say a few words about it, about approximation theory. And other places where it shows up are things which we will see for sure in what we do, and that's in harmonic analysis, which is closely connected with Fourier analysis. And certain kinds of system theory, namely linear system theory for linear systems with for time invariant linear system. Okay, so these last two, we're going to see how convolution comes up. And I would say that you can spend a lot of time trying to explain what convolution is by drawing pictures. And in the lecture notes that attend this course, there's examples of this, and maybe you'll get some intuition from that, or maybe you won't. But I would say the best thing to do to come to grips with convolution, I won't say understand it, because I don't know if I'd be prepared to say that I understand it, is to just sit with it, understand some of its properties, see how it's used, and then after a while you become familiar with it, which is again not necessarily the same thing as understanding it, but there's lots of things that are like that. You get familiar with them without necessarily understanding them. So if you're looking for a quick intuitive explanation for how to understand convolution, this isn't the right place. All right. So convolution for us will come in two basic flavors: continuous time and discrete time. And what I'll do is kind of give the basic formulae for each of these. We'll see variations of these that are different, but just to get an idea of what convolution looks like. So in continuous time, convolution takes two continuous time signals, f and g, and returns their convolution, which is denoted with f star g. Okay, and the definition is that this is, sorry, I need to evaluate this at t. Okay, and this is the integral over r, f of t minus s, g of s, yes. Okay, and the discrete time has a similar formula, where, of course, the continuous time t is replaced with discrete time, and so discrete time means we're working on a sampled a discrete sampled time domain with sampling interval delta. So every time looks like that. Okay, and the convolution looks like this. Okay, so as opposed to an integral over r, it's a sum over z. And so it's f of k minus j delta g of j delta, like that. Okay, and so you can see that these are really just two versions of the same thing, where one has a sum and the other one has an integral. certainly that you can't glean much from looking at the formulae. But let's see what we can glean. Okay. So the curious thing here is what it does to, say, F. So we're going to see that F star G is G star F, and so you could just as easily write this as G of S and sorry, F of S and G of T minus S. But the point is that this operation of using the argument of T minus S, it appears in one of either F or G. And this does two things. So remember here that the integration variable is S. Okay. And so with respect to the integration variable, we're flipping time, okay, because it's minus S here in the argument of F, okay? So F is having its graph flipped and translated by some T, okay? And so it's kind of a strange thing that you're doing here, flipping and translating. Okay, especially the flipping part that seems quite counterintuitive, but it's exactly that which, for example, leads to the very useful causality properties that convolution has in system theory. Okay. All right. So let me not say very much more about that. Instead, let's start by talking about continuous time convolution. Right. So it's kind of the harder one, and because it's harder, it's actually better to talk about it first. Discrete time convolution hides some of the interesting stuff about convolution. So we're going to look at the more difficult one first, namely continuous time convolution. Right, and then discrete time convolution will follow super fast from that because it's quite a lot easier. Or at least there's some technicalities you don't have to fuss with. Okay. All right. So continuous time convolution. Now, continuous time convolution can have in itself different versions which don't look like that. Okay, there can be a periodic convolution. Okay, and there can be convolution, and we will see that today of signals whose support is restricted in some way. Okay. And so the point is that not all convolutions, even in the continuous time case, are going to look just like that. All right, but we'll start with those that do. All right, so given F and G, and I don't want to really at this point put any properties on F and G. Let me just proceed with general sort of properties of F and G, and then make definitions as we go along to make things work. Okay, so given F and G, denote D of F and G to be so T's in R. Okay, so the first thing is you need to be able to do this integral. Okay, and so T with respect to this integral is fixed, and so when you fix a T, it has to be the case that as a function of S, the corresponding integral exists, and so that simply means that this function S goes to F of T minus S, G of S is in L1. Okay, and we'll think of convolution here as these signals as being possibly F valued. Okay, so to calculate the convolution integral, you need for t to be in here, or else the integral doesn't make sense in the usual sense, at least. Okay, and we'll say that f and g are convolvable if a set of points where not in here, okay, so where this thing is not in L1, okay, has measure 0. Okay, and so the point is we can do this calculation for almost every t, right? And if we can do that calculation for almost every t, then we'll say that f and g are convolvable. Okay, so if fg is convolvable, and so sorry, I shall use the better terminology here. So we're going to say the pair fg is convolvable, if that's true. All right, so if fg is convolvable, then this formula then makes sense. Okay, for almost every t. And there may be some set of measures 0 of t's for which that formula doesn't make sense. And the value of f star g at those points, we don't really care what it is. Make it 3, make it 0, because we're kind of thinking about the Lebesgue theory here, and so we're only interested in functions defined up to sets of measures 0. Okay, so we don't bother ourselves with points that are not in d of fg. Okay, all right. Okay, so one of the things we're going to do is we're going to talk about sufficient conditions for convolvability. But before we do that, let's maybe look at an example. And the example is really intended to kind of give you some feeling for how convolution works. And I'm going to draw the graph of the example. Okay. And so it has a value of 1 between -1 and 1 and 0 otherwise. Okay. All right, so let's look at f of t minus s. So what's that going to be? Well, what that is going to be, so this example is a little bit degenerate in the sense that f of s is equal to f of minus s. It's although my drawing doesn't show that very well, it's symmetric if you flip its graph about the the dependent variable axis. Okay. But nonetheless, for a fixed s, okay, well, let's maybe take s equals 0. Okay, so for s equals 0, sorry, I take that back. For t equals 0, then f of s is going to be the same as g of s in this. So sorry, I'm interested in calculating. I didn't say this. The convolution of f with itself. Okay, so f and g are the same in this little example that I'm thinking about. And so when t is equal to 0, for example, this thing is f, because f of minus f is f of s, and so it's really the integral of f squared. But the integral of, but f squared is f, so really this is the integral of f. And so we know that at t equals 0, for example, it'll have the value 2. Okay. All right. So then what happens as you move t is that the graph of f kind of gets shifted. Okay, and then you do the integral. So when you shift for large t's, eventually the graphs of the shifted function and the graph of f will not overlap, and so the resulting product of f of t minus s times f of s will be equal to 0. Okay, and so it's only going to be for t's which are small enough that I get an overlap between the two graphs that are going to contribute to f star f. And if you think about that for a second, what that means is that this will be defined for t, or sorry, it'll be non-zero for t between -2 and 2, because as soon as I shift by more than 2, then the graphs are going to not intersect, or sorry, not overlap. Okay, okay. So the point is, at the end of the day, I've sort of babbled about what the answer should be without actually just calculating it, which you could also just do, right? You can just calculate the integral. You can just calculate this integral easily enough. Okay, but my sort of yammering makes this believable, maybe. Okay, so we decided that at t equals 0, it has the value 2, and we know that outside -2 and 2, it has the value 0. Okay, so I'm plotting here f star f t. Okay, and then what happens is for t's that are near 2 and -2, then the overlap is going to be very small. Okay. Okay, and then the value of the integral is going to be small. And in fact, it not hard to see that it grows linearly. Okay, and so the graph looks like this. All right. Now I wanted to chat about this rather than just do the calculation. Again, to try to maybe get a little tiny bit of feel for what happens here. And so we can see that two things are showing up in the convolution. Okay, one has to do with the support. Okay, and my chatting was meant to indicate how the fact that f has a compact support leads to support constraints on the convolution of f with itself. Okay, and you indeed see that, right? And then the other thing was that when you get close to the boundaries of the support, okay, the overlap became very small, and so you get a continuity in the convolution that f doesn't have. Okay. All right, so we see that in this example, at least, and this isn't a theorem. This is just an observation that holds in quite a few examples, is I guess how I would say it. In this example, we see that the convolution does two things. It smears the support, Okay, so it takes something which has a support between -1 and 1 and smears it out. Okay, and 2, it smooths the function. Okay, so by convolving two discontinuous things, in this case they happen to be the same, but no matter, you end up with something that's continuous. And let's say that that means that it smooths it. Okay. All right, and these are features that you often will see with convolution, and sometimes there's theorems that go along with these observations. Okay. But there's definitely not a theorem that holds for all convolvable pairs. Okay. All right, so there's an example to kind of give us an indication of what happens. Let me now give some general properties of convolvable pairs. Okay, the first is the convolution when it exists, okay, because you can have F's and G's that are not convolvable. It's easy to come up with examples of F's and G's that are not convolvable. So for example, if you want an easy example of something that's not convolvable, just take the constant function F from -infinity to infinity, right? So when you form this product for every t, it again will just be the constant function 1, which is not integrable over R. Right? So it's very easy to construct examples of things that are not convolvable. All right. So, but if Fg is convolvable, then GF is convolvable. Okay, so really the role here played by F and G that's different is which one takes the t minus s argument and which one takes the s argument, and but this just tells you it doesn't matter. And F star G is equal to G star F. Okay, so convolution is when it exists is symmetric. Okay, if it's also linear, okay, so if Fg and this is this is very elementary. It just follows from a change of variable. Okay, and similarly, this is elementary. It just follows from the linearity of the integral. So if Fg and Fh are convolvable, then Fg plus H is convolvable. And of course, F star G plus H is F star G plus F star H. Okay. All right, so convolution is not generally associative, okay? It is not generally true. That F star G star H is F star G star H, even when the formula makes sense. It's well defined. Okay. So there are, and we will see many classes of spaces of functions, signals, for which that is true, okay? And that leads many authors to assert that this is true in general, but it's not. Okay. It's true in the cases where convolution typically gets used, but as you know, a general operation on convolution, that's not true. Okay, so you have to think a little bit to come up with counterexamples, but they're not all that exotic. Okay, so if fg is convolvable and if both f and g are locally integrable, then f star g is locally integrable. Okay. So this gives you some attributes of the convolution as a signal itself. Okay, at least you know that it's locally integrable. Okay. And this is actually a surprisingly touchy little thing. It's not easy to prove. You have to do some work to show that. Okay, so in this example, we had some observations that we made about support, okay, and support of the convolution, right? So let's look at that in a general setup. Okay, so if f is in L1 loc, denote sigma of f. Okay, so sigma of f is going to be the largest time, so the sup of all the t's in R, so that f of s is equal to 0 for almost every s which is less than t. Okay, so the idea is, you know, you take a t, ask if to the left of t, f is almost everywhere 0. Okay, so then you include t in the list of things you're going to sup over, and then you sup over that. Okay. Okay, so this is kind of like the left boundary of the support of f. You have to be careful defining the support of a discontinuous function, as a thing in L1 loc generally is, but you can think of this being the left boundary of the support. Okay. All right, so what I claim that if f and g are locally integrable and if they have support which is bounded on the left, so that means that this quantity is not equal to minus infinity. Okay, so if sigma of f and sigma of g are greater than minus infinity. Okay. So get my grammar right. And if fg is convolvable, then there's a formula for its convolution. again, this is intended to generalize this observation I made in this example about the support here and how it relates to the support there. Okay. All right. So it's equal to the integral from sigma of g to t minus sigma of, sorry, that's not t, that's g, sigma of f. Okay, so it's kind of a funny looking formula. Okay, just remember that sigma of f and sigma of g are just, you know, fixed numbers. Okay, of the normal argument that you have for convolution. Okay, and this is true when t is greater than or equal to sigma of f plus sigma of g, and it's 0 otherwise. Okay. All right. So let's see why that might be true, because this is weird and a little bit confusing. And one of the main consequences of this is that the convolution integral in this case is done over a compact set of times. Okay. All right. Okay. So let's see why this is true. Okay, so to see this, let's okay, so let's let t be in this case. Okay, so t is less than that. Like so. Okay, so I'm going to break this into two special cases. First, I'm going to take sigma of g, sorry, s less than or equal to sigma of g. Okay, so then I'm going to sort of be a little tiny bit careless here. So remember that sigma means that this is equal to 0 for almost every s. I'm just going to go ahead and assume that it's equal to 0 for every s, which I can do without loss of generality here because I'm, you know, integrating. It just saves me from having to fiddle around with almost everywhere stuff. Okay, and so the point is that if s is less than sigma of g, then g of s is equal to 0. You know, and generally it would be for almost every such s that would be true. And so I don't want to have to mess around with that. Okay, so then the point is g of s is equal to 0. Okay, and therefore, okay, so oops. Okay, and so when doing this integral, therefore, okay, that ensures that my lower bound I can take my lower bound to be sigma of g. Okay, good. Then I have the other case to consider in this special case, which is when s is greater than sigma of g. So if s is greater than sigma of g, okay, then, okay, so I'm taking this, okay, so, and all I'm going to do is subtract s from both sides of that formula. Okay, so t minus s is less than sigma of f plus sigma of g minus s. Okay, and my assumption on s now, that one, implies that that quantity is non-negative. Okay, and so therefore this is less than or equal to sigma of f. Okay, and then that would imply, right, that f of t minus s for t less than this and s greater than that has to be to the left of the left boundary of the support of f, and so f has to be 0 there. Okay. All right, so that means that that this okay, sorry. So that means that this integrand will vanish whenever that's true. Okay. All right, and so then what I need to do is I need to ensure that for t's greater than this, okay, my integral takes place over these limits. Okay, and it's the upper limit here that I have to worry about, because the lower limit is obvious, right? Because for s is less than sigma g, as we've already seen, that's equal to 0. So what we're going to do is we're going to see that when t is greater than this, then the upper limit can be taken to be that. Okay. All right. Now, if t is greater than or equal to sigma of f plus sigma of g, okay, then, all right, if we have, sorry, let me say it this way, and if, okay, so we're integrating here with respect to s, okay, suppose we have s larger than that, okay, so I'm going to show then that the integrand is going to be 0 for those s's, okay, so and if s is greater than t minus sigma of f, then t minus s is less than sigma of f, okay? All right, just manipulate these two inequalities. And so then f of t minus s is equal to 0, okay? And so for t is larger than this integral, the integrand for this integral, it will vanish for s's larger than that, okay? And so the point is that the integral can be taken to happen over this compact subinterval, okay? All right, so that's a very peculiar and special formula that shows up in cases of convolution where the support is bounded on the left. And that's a very important special case in system theory especially, okay? And so let's look in the case when sigma of f is equal to sigma of g is equal to 0, okay? Then f star g of t, and here I can really do that if I want to, okay? Can be taken to be the integral from 0 to t, okay, because of this, okay. F of t minus s, g of s ds, okay, and this is true when t, okay, and so here t is greater than or equal to 0, and 0 otherwise. Okay. All right, so this formula is a formula that might look familiar to you because it's a kind of convolution formula that shows up when one looks at the variation of constants formula in solutions of ordinary differential equations. And so maybe we'll look at this in detail later, but I'll recall it here just to cement this if you have seen this before. Okay. Okay, the solution to the initial value problem x dot. So I've already introduced my c's instead of x's, so I'm gonna do that. Okay, so I'm looking at a system of linear constant coefficient ordinary differential equations, rather like we looked at last time. So A is a linear mapping. Okay, plus let's say f of t. Okay, with the initial condition that x of 0 is equal to x naught. Okay. Then for t greater than or equal to 0, the solution is, okay, so it has two parts. It has a homogeneous part, which is just the solution of the homogeneous equation with this initial condition, plus integral from 0 to t, e to the a, t minus tau, f of tau, d tau. Okay, and the point is that this is a convolution rather like this. Okay, all right. Okay, so now what I will do is I will look at some special cases of convolvable pairs. Okay, so conditions on F and G, sometimes they're the same condition on both, sometimes it's a different condition on F and then another condition on G to ensure that the pair is convolvable. Okay, so convolvability of continuous time signals. Okay, and so there's no, as far as I know of, no useful class of signals for which that are convolvable. What one does is one picks out special classes that have interesting properties related to the things that you're interested in that are convolvable. Okay, and so that's what I'm going to do. I'm going to just give you some special classes that are. Okay, so here's one. And these, I'm going to state these as theorems. They're not generally that hard to prove. Okay, so if F and G are in L1, then the pair FG is convolvable. Okay, so this follows from what's known as Fubini's theorem. For showing that wherever it is, you want to show that this integral. Oh, sorry. Yeah. So. Right. So Fubini's theorem shows up if you want to show that this thing is in L1. And so the way you show it is in L1 is you have to integrate this dt, and then you use Fubini's theorem to show that that integral is finite. Okay. Right. And so that also gives you the convolvability of F and G. Okay, and so as I just argued by Fubini's theorem, the convolution of F and G is in L1. Okay, and moreover, so let me introduce another H in there. Okay, convolution in this case is associative. Okay. All right. So this gives you a class then of convolvable signals, namely where F and G are both in L1. Okay, so that's nice. L1's a nice identifiable class of things. Okay. And so what this tells us is that L1 has a product, right? So there's a way of, excuse me, there's a way of taking a product, namely convolution product in L1, and you stay inside L1. Okay, and so this turns L1 into what's called a ring, and a ring has a sum and a product. Okay, so we already know that L1 has a sum, and now we know that it has a product. Okay, but the product is not as nice a product as you might like. So let's maybe look at some of the kind of algebraic properties of this product. Okay, so this gives L1 of RF the structure of a ring, meaning it has addition, which is normal addition, and multiplication, which is convolution. Okay, and in a ring, you know, these structures of addition and multiplication have to fit together in the usual sort of distributive ways that I'm not going to list here carefully, but you can guess what they are. Okay. Okay. This ring has no unit. Okay, and by that I mean a multiplicative identity. Okay, that is, there is no U for unit, so that when you multiply it by any F, you get back F for every F in L1. Okay, so indeed, such a U must satisfy integral over R F of T minus S U of S ds is equal to F of T, okay, for almost every T. Okay, so in particular, at T equals 0, this gives integral over R F of minus S U of S ds is equal to F at 0. Well, this, except for this minus sign here, which is of not much significance, this looks rather like the condition of the Dirac delta, right? So it takes an F and gives you the value of F at 0. And this isn't a proof that this thing doesn't have a multiplicative unit, but it certainly suggests why that might be the case, right? Okay, this. I'll sort of summarize that by this. So it's Dirac-y, meaning it looks like U is trying to act like the Dirac delta function, which we know there is no such function. Okay, another not entirely nice property of multiplication is that there exist F and G in L1 for which F star G is equal to 0. Okay. And so, this has to do with kind of the invertibility properties of multiplication, right? Is there a multiplicative inverse? And this shows that there cannot be, right? Because there's no way to recover F or G from a formula like that by inverting one. Okay. Oh, so I should say there exists non-zero. Otherwise, that's obviously true. Okay. All right. So this means that L1 of RF as a ring is not what's called an integral domain. Okay, so an integral domain is just a ring which for every non-zero F and G, their product is not zero. Okay, so yeah, the convolution product does not have that property. All right. Okay, and taking convolution doesn't leave anything out. Okay. So what I mean by that is that if H is in L1, then there exists F and G in L1 such that H is F star G. Okay. All right, so by taking convolution, you're by considering convolutions of things, you're not excluding anything in L1. Okay. All right. All right, so that is one important class of convolvable signals, L1. Here's another important class, and this one's going to be very tightly related to this this observation here. Okay. All right. Okay. So if F, G, H are in L1 loc of, okay, so I'm changing my previous example in two ways. One is I'm restricting the class of signals in the way that I'm not considering signals defined on all of R, but only those defined for positive times. Okay, but by doing that, I gain enormously, actually, in the kind of flexibility in terms of the signals by extending from L1 to L1 loc. Okay, so it's certainly not the case that you can leave off this and have L1 loc, the convolution of two things in L1 loc being defined. Okay, you need to put some restriction on the supports. Okay, and the reason is connected to the fact that by restricting the supports of F and G, you restrict, you don't have to do this integral over an unbounded domain. Okay, so the local integrability is enough to get you what you want. Okay, all right, so then So we have a statement rather like the one we had for L1. So FG is convolvable. The convolution is in L1 loc. Okay, and the convolution is associative. Okay. And again, these facts are not difficult to prove. You prove them in rather the same way, just taking advantage of the fact that the support is bounded like this, which gives you this formula for the convolution in that case, right? But the idea of the proof is the same as it is in the L1 case. Okay, and there's also a corresponding set of properties like these three. Oopsie. Okay. But there's an important difference, and that is 2. Okay. In the case of this restricted on the support to be just positive reals, it actually is an integral domain. Okay. So so let me say that without rewriting all of the stuff that I wrote already. So one has properties analogous to 1 and 3 for L1 above. However, for 2 in L1 loc, we instead have 2 prime, which is that if F and G in L1 loc are non-zero, then so is their convolution. I.e., L1 loc is an integral domain, okay, as opposed to L1, which is not. With the convolution product. Okay, so this rests on what's known as the Titchmarsh convolution theorem. And it's possible I have an extra S there, I don't know. Okay. So the Titchmarsh convolution theorem is one of those theorems which is very easy to state. Okay, it just says exactly this. Okay, but it's hard to prove. Okay, so this is one of those, and some people put in some time every now and then to try to see if they can produce an easier proof of the Titchmarsh convolution theorem. And there are digestible, more and more digestible proofs, but I wouldn't say any of them are easy. Some of them might be elementary, meaning you can prove it without digging deeply into anything exceedingly complicated, but none of them would qualify as being obvious. Not a good candidate for a final exam question. Okay. All right, so this is now two classes of signals which are convolvable. Okay. Now, in both of these cases, they had the property that both pairs in the convolution product were in the same space. Okay, L1 and L1 log. Okay. Now we're going to look at cases where the conditions on each term in the pair are different. Okay. All right. So third convolvable pair theorem. Okay. All right. So there's this peculiar condition that shows up, and it looks like this. So the condition is that 1 over P plus 1 over Q is equal to 1 plus 1 over R. Okay, so if you know a bit of functional analysis in your spare time, you'll be familiar with a condition like that, but it's different here. Okay. All right, so given a P, a Q, and an R, and I'm allowing infinity here, right? So 1 over infinity being 0. Okay, so if F is in LP, the real line, and G is in LQ on the real line, then FG is convolvable and the convolution F star G is in LR. Okay. All right, so there's no ring structure here, right? There's no product because F and G generally are going to sit in different spaces. And even if F and G happen to sit in the same space, so if you're in a case where P is equal to Q, let's say, the convolution will not be in that space. Okay. Okay, so I won't say too much about that, but just to consider some special cases. All right, so one special case is when, so if Q satisfies 1 over P plus 1 over Q equals 1, okay, we say that Q is what's called, it's just name calling, the conjugate index of P. Okay. All right. And so in that case, and we denote, because it just depends on P, and we denote this by P prime. Okay, so now if Q is P prime, okay, the conjugate index, okay, then it must be the case from this equality, right? So 1 over p plus 1 over q is already equal to 1. So this must be 0. So it implies immediately that r is equal to infinity. Okay. But even more is true in that case. Okay. Then the convolution is in L infinity. That's what the theorem says, but more is true, that f star g is actually continuous and in L infinity, which is the same thing as saying that it's in C0 bounded. Okay. So that's one special case. All right. And another special case is when q is equal to 1. Okay, then, okay, so let's take a look at the formula here. All right, so q is equal to 1, and so this is going to cancel with that, and so p must be equal to r. Okay, so this means that if you take the convolution between something in LP and something in L1, the result will be in LP. Okay. All right. Okay, and then you won't be surprised to know what comes next. What comes next is the version of this for signals that are have their support contained in positive times. Okay. All right, so finally, for today, again, I'm going to let P, Q, and R be in here. Okay. So if F is in LP loc, okay, of RF, sorry, positively supported, and if G is in LQ loc, then okay, F and G first is convolvable. And the convolution is in LR loc. Okay. And the special cases are the same as above. I should be explicit though. It's not C0 bounded, right? Because when, so in the, so here, let me write it out. Okay, so special cases. All right, so when Q is equal to P prime, the conjugate index, okay, then, okay, so what do we know, okay, just from the statement of the theorem? So again, if Q is equal to P prime, then 1 over P plus 1 over Q is equal to 1, and so R must be infinity, okay? And just like in the case above of signals defined on all of R, but without being locally integrable, we had in this case that the convolution was continuous and bounded. Here, it should be an L infinity loc, okay? But L infinity loc just means bounded on every compact sub interval, okay? So it could possibly be unbounded, but bounded on every compact subinterval. And so what we expect to happen is that we should have continuous functions that are bounded on every compact subinterval, but that's just the same as continuous functions because every continuous function is bounded on every compact subinterval. So the point is that, oops, f star g is in C0. Okay, and then in the case 2, where q is equal to 1, we get r equals p again. Okay. All right. So we're going to see how these things show up for us in multiple ways. So this kind of convolvable pairs business is going to be important for us when we talk about system theory. Convolution as an operation is going to become important for us when we talk about Fourier analysis. Okay. But here I just want to sort of get some of the basic stuff about convolution sort of out there so that when we come across it later, I can make reference to it. All right, so next time, what we will do is we will talk about continuity of the convolution operation, okay? And so we'll do that in the continuous time case. And then after we talk about continuity of the convolution operation for the continuous time case, then we will talk about convolvable discrete time signals, and we'll see that the discussion there is follows along rather similar lines to what we've just done in the continuous time case.